Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, we'll be working about stresses in soil mass, which means like when we apply load onto soil, let's say from that building or like a column, then you can see the soil pressure changes as it goes down here. And the pressure, let's say here, is 3 psi, it's like 6 psi, and at a certain distance, you will see there is no influence of that force in the soil layer, okay? Similarly, they are showing like three different cases, like hard soil or dry soil. This is normal soil with water content, means like moist soil, and this is completely wet soil. So you can see, based on the soil property, this one can propagate a little bit more if the soil is wet. On the other hand, you can see if the soil is hard soil, then basically it doesn't propagate that much. So in this chapter, we'll just try to learn how we can find out the stresses because of the load that's coming from any infrastructure. That's the first thing. At the same time, we'll try to learn how the load will be transformed in other axes, like and how this one will affect the strength of soil. Okay, let's move forward. So you were already familiar with that stress transformation thing. You learned that one in your mechanics of solids class, okay? So you can see this is an element here, which has like here is sigma x, this is sigma y, this is tau xy, this is tau xy. Similarly, this is sigma y, this is sigma x. And then you try to see that what would be your normal force and shear force, let's say at EF plane. Then basically we cut along that plane. The force normal to that surface is called the normal stress, and anything parallel to that surface, we call that one tau n, right? And we already developed that equation. You already know that one from your mechanics of solids, that your sigma n on normal stress at EF plane is basically sigma y plus sigma x divided by 2 plus sigma y minus sigma x divided by 2 cosine twice theta plus tau xy sine twice theta. And the shear stress at that plane, that has to be tau n is equal to sigma y minus sigma x by 2 sine twice theta minus tau xy cosine twice theta. And the angle of principal stress tan twice theta is 2 tau xy sigma y minus sigma x. Now, this one is not exactly what you learned from your mechanics of solids. There is a little bit difference here in terms of your sign convention, okay? That's why this equation might be a little different than what you see in your mechanics of solids class, okay? Now, if you want to use this formula to find out your normal stress and shear stress in any particular plane, then basically you have to remember three things. What are the three things you have to remember? First of all, that compression is positive here, okay? You can see in your mechanics of solids book, actually tension was positive. Here, compression is positive because soil is not allowed to, subjected to any kind of tension because it doesn't have any tensile strength. So most of the time it's compressive strength. So that's why they assume that one positive. Then the angle theta is measured. Theta is the angle of the inclined plane, like at which plane you are trying to find out your shear stress and normal stress, right? Let's say EF plane. Now this is your angle theta with the x-axis, positive x-axis. So we measure our theta from the positive x-axis counterclockwise. Okay, counterclockwise is positive. If you measure clockwise, then basically that has to be negative. Okay, so that's the angle thing. And then right side upward shear is positive. You can see this is upward here. We are assuming this one is positive. Right side upward, okay? Right side upward is positive. If this is downward, then basically your shear stress would be negative. So if you remember that three things, then basically you can just use this equation to find out the transform stress at any particular plane, okay? Now let's see some example, okay? Like if it's given here, then basically what are the values of like sigma x, sigma y, theta, and tau xy, okay? So you can see here for, let's say for A, for this one here, you can see your sigma x is 162 and sigma y is 128. And both of them are compression. So basically this is positive, okay? So you can see our sigma x 162 kilonewton per meter square and sigma y is 128 kilonewton per meter square. Now, what is our theta? They gave me this 55 degrees, but that measured from there. But from the basic, like definition or the figure that we developed that equation, basically measure that one from here to that particular plane, okay? So this one is like this, okay? And then this angle is theta here. And you can see this theta is basically 90 minus 55. So that theta is actually 35 degrees, okay? Now you can also see that tau xy is actually right side upward. So your tau xy has to be 32 kilonewton per meter square, okay? Now let's see for B. You can see here for B, your sigma x is 9.6, sigma y is 2.4, and you have to measure your angle like this one, and this one has to be equal your theta. Now you can see that this angle is 60, so this angle is 60, and the total is basically 180. So if you take 60 out of 180, then you get 120. So that's the one way you can do that. You can do that one in another way. So you can extend that line AB, and then you can measure that one clockwise, and then you can say like, hey, this is negative theta here. So if this is 60, then basically this is 60. So your theta has to be negative 60. So if you use 120 or negative 60, basically you are gonna get same answer, okay? And here you can see your tau xy at the right side is downward, means like negative, okay? So your tau xy is basically negative 2.4. Now, once you get these values here with their proper, like sign convention, then basically you can just plug them in the equation and you can find out the normal stress and shear stress there, okay? Now here is the example here, that a soil element is shown in figure 1. The magnitude of a stress is sigma x equal to 120 kilonewton per meter square, tau equal to 40 kilonewton per meter square, sigma y is 300 meters square, and theta equal to 20 degree. Determine the magnitude of the principal stresses and normal and shear stresses on plane AB, okay? So you can see here, actually, this is sigma x positive here, sigma y is positive here. This angle is 20, which is fine, but your tau is basically downward, means like actually this value is negative 40 kilonewton per meter square, okay? So if I do the solution here, your sigma 1 by sigma 3 is basically principal stress is sigma y plus sigma x divided by 2 plus minus root over sigma y minus sigma x divided by 2 square plus tau square xy. So if you plug all those values here, you can see they plug the value of tau xy negative 40, okay? All other are positive. So basically it doesn't matter though for principal stresses because this is a square term. So negative and positive actually goes positive all the time because of the square sign. So your sigma 1 is 308.5 kilonewton per meter square, and your sigma 3 is 111.5 kilonewton per meter square, okay? Now we have to find out the normal and shear stress at plane AB. So we already know the equation that your sigma n is equal to sigma y plus sigma x divided by 2 plus sigma y minus sigma x divided by 2 cosine twice theta plus tau sine twice theta. So if you plug the value of sigma y and sigma x, this is your theta and this is your tau xy, then basically you get 253.23 kilonewton per meter square. Now, once again, if you make a mistake here, like if you don't use that negative sign there, then basically you are gonna get wrong answer, okay? And once again, like you know your tau n equal to sigma y minus sigma x by 2 sine twice theta minus tau xy cosine twice theta. So if you plug that value here, again, this tau xy is negative here. So you got 88.4 kilonewton per meter square, okay? So that's the easiest way to find out your stress transform in any particular plane, okay? Now, many cases you will see, especially for soil, that we don't apply any shear force here. All the structure, the load is coming vertical because of the weight of the structure, right? So that's why we are talking about simplified stress transformation. Means like when we use the knowledge of stress transformation in soil mechanics. Okay, you learned that one for mechanics of solids, and that was like very broad and general. In soil mechanics, actually, we never apply tau xy here. We only apply compressive force from the weight of the structure, which is sigma y. And this is the reaction of the soil when we apply that load, okay? So you will see that although I didn't apply any shear here, but this one will create shear along the AE line, okay? So you can see if your tau xy equal to 0, then basically let's say DC and BC plane, they don't have any shear stress. This means these are principal plane, right? So you can say in that situation, sigma y is actually your sigma 1 and sigma x is equal to your sigma 3. And the normal stress at EF plane, actually that's AE plane, that is sigma normal is sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 plus cosine twice theta. We had like the tau part here, but now this one is 0. So this is kind of the simplification of that. And you can see the shear stress at the plane is actually tau n equals sigma 1 minus sigma 3 divided by 2 sine twice theta. And there was a tau term here that's actually 0 now. And you can see the angular principal plane is 0, okay? So basically this is the principal axis here, okay? Now let's see, like sometimes we can do that one in terms of graphical method, right? And we call that one Mohr Circle. You already learned that one, that how to develop your Mohr Circle. Sometimes if you want to do that graphical method, then basically you can always do that, okay? So in that situation, like if I know this is my, element, and then this is like I took the EF, I cut an imaginary section at EF and then show that one as normal force and tau force, then if I want to draw the Mohr circle, then basically the center of the Mohr circle has to be sigma x plus sigma y by 2, 0. Okay, this is my sigma axis, this is my tau axis. Okay, so the center is sigma x plus sigma y by 2, 0. So that's basically your center. Then what is your radius? Your radius is root over sigma x plus sigma y by 2 square plus tau x y squared. Once you get that radius and you know the center, so you can just draw the Mohr circle. Okay, so if you draw that Mohr circle, then basically you can find out the, like each of the plane here and find out what would be your normal stress and shear stress in that particular plane. So how do you do that? Once I draw that one, then basically you can see that counterclockwise is positive shear now, okay? Counterclockwise is positive shear. So for this one, you can see that this is sigma x, that BC plane, the stress is sigma x and tau xy is positive. So sigma x plus tau xy. So that's the point like for BC plane. And then if you draw that line here, then basically you get your point M. That's actually here. As I said, that counterclockwise is positive. So here, this one is clockwise shear. So that's why this one is negative sigma y and then minus tau xy. Okay. Now, once you get that plane here, actually you can see here that BC and DC is actually 90 degrees from each other, right? But Mohr circle always draw that one double. Angle would be always double. So that's why you see from here to here is actually not 90 degrees, it's 180 degrees. Okay. Now you can see from that plane DC or like AB, actually your EF is making theta degree here, okay? So from that particular plane, which is actually AB plane or like BC plane, you can just get like twice theta angle here. I'm just doubling that one because it's theta, it has to be twice theta. And then if you draw that line here, then basically the Q is the point that represents the normal stress and shear stress at EF, okay? So here is your sigma n and tau n, okay? So this is a graphical method. You can just try to see that what is the location of Q and then measure that one from the graph, or you can just count that one, how many, like what is the value of sigma n and tau n from there, okay? So that's basically your Mohr circle. Now you can see here that you can also do that one. Let me not explain that one. That would be a little complex, but we don't need that one in like that much. So let me go to the other one, which is very kind of normal. That's the Mohr circle for simplified case. We said that like usually we don't apply shear force at the surface of the soil, right? So no shear force here. So in that situation, you can see this is sigma 1 and sigma 3. That's basically your sigma 3, and this is your sigma 1, and this is your principal stress, principal plane here. Okay. And if you want to find out like that theta here, you just get twice theta from that principal plane, and you get this Q here. Okay. So it's a little bit easier to do that. Okay. Now we can see the other method, which is called the pole method, which is very, very common. And we usually use that one in soil mechanics quite often, okay? So how do you find out the pole method? You can see here, this is the element here, and let's say this is my Mohr circle given here, or you can just draw that one by yourself. Now you can see, to find out the pole, you just try to see either this one or this plane, any one of the planes here, okay? So here you can see this is 90 and minus 60. So this one is basically 90 and minus 60. Once you get that point here, then you have to draw a line which is parallel to B and C, okay? So if you draw a line, vertical line here, then basically you get this point P, which is called the pole, okay? So pole is a unique point for any particular, element. Once you get that pole, you can find out the normal stress and shear stress on any particular plane. What you have to do only, like, draw a parallel line from the pole with this AC, okay? So if you draw that parallel line here, then basically 45 degrees, this one touches here. So if you just try to see that what is your sigma X and sigma Y here, that's basically 60 and 30, okay? Now, if you know your pole, then basically you can do that one other way too, like rather than using this one, you can use this one. Here is at 150 and positive 60 because this is counterclockwise. So 150 and 60, and then draw a line parallel to DC. So this one is drawing that line. So this is your P, okay? Similarly, you can draw that one from here, but whatever way you draw, your P is always a unique point, okay? Now let's say I'm trying to find out the normal and shear stress at this plane DE, okay? Then what I have to do, I have to draw a line from P, which is parallel to DE. So that's basically the point, and I have to measure that what is my normal stress here and what is my shear stress here. And basically I can get the answer quite easily without any calculation, okay? Now, a stress caused by any load, that how far the load goes, how this one propagates, okay? So if you want to see like at different layers here, that how far this one can go, it's always a big challenge to find out that how far this load will go and what will happen at your sigma X and your sigma Y. I mean, stress in the X direction and Y direction. But Bossinus, one of French, scientist, he solved the problem of stress produced at any point in the homogeneous, elastic, and isotropic media as a result of a point load applied on the surface of an infinitely large half sphere. Half sphere means like if you take a sphere, cut that one, and then you just put that load there. So he is coming from the very theoretical method, and he's using basically the mechanics of, elastic theory, okay? So he developed that one. And then, although the soil is not perfectly homogeneous, elastic, or isotropic medium, but Bossinus equation provide quite reasonable answer for soils, okay? Maybe one of the best. There are several methods too, but this one is one of the best, even though our soil doesn't exactly qualify the assumption on which the Bossinus equation is based on, okay? But we see that Bossinus equation provides quite reasonable answer. So we are just using these methods to find out that what would be the stresses at different location because of the load on the surface, okay? Now, this one is saying that stress caused by a point load. So if you put a point load here at the surface, you will see at the bottom here, like a different location. So you were showing a location here, which is actually X, Y, and Z direction, okay? The location of that point is, let's say, X, Y, Z. So you are trying to find out what would be the change in effective stress, change in stress here because of this load here, okay? Now, let's say the load is not here yet, but you were talking about a point here. And definitely this one has some pressure because has some low stress here because of the load of the soil itself. So if that height is Z, then basically the vertical stress is gamma Z. Gamma is the unit weight of soil, okay? Now, once you add the P force, then basically this one has some impact on that point A, okay? So that's what we are trying to see, that what would be the impact of point P, which is a point load at any particular point below the soil. So del sigma Z means like change in your vertical stress is this thing here, okay? But we simplified that one and we are assuming that the whole thing here is actually I1. So your del sigma Z is equal to PZ square I1, okay? Now what is I1? I1 is this part here, okay? 3 by 2 pi 1 plus r by z squared plus 1 to the power 5 by 2. Now, your I1 is a function of r by z, where r is nothing but root over x squared plus y squared, okay? So r is the distance from here to here, okay? So this is nothing but x squared plus y squared, okay? Now, you can either use this equation directly in your Excel sheet, and if you change your xy, your r will change, and this value will change too, okay? But this book, they provided a chart for I1 here. That's the variation of I1 for various value of r by z, okay? So if your r by z equal to 0, then your I1 will be 0.4775. R by z, you can just read this, is 0.34. Then basically your I1 has to be 0.3632. And then you can see your RZ, they are showing that one R by z up to 0.5 here. But if it doesn't cover here, actually you can just make your own table, or you can just calculate directly from that equation, okay? Now let's see here. So that's an example problem here, okay? Example problem for a stress caused by a point load. So consider a point P equal to 5 kilonewton, then figure 10.7, which is nothing but this figure here. This figure here. So they have to give you like P and X, Y, Z. Once you get that one, then you can find out the change in vertical stress because of that particular point load, okay? So they gave you, like they are asking you, like calculate the vertical stress increase del sigma Z at Z equal to 0, 2, 4, 6, 10, and 20 meter. Given X equal to 3 meter and Y equal to 4 meter. So if X equal to 3 and Y equal to 4, then your R is root over X squared plus Y squared, which is 3 squared plus 4 squared is 5 meter R, okay? Now, if your R is 5 and your Z is 0, 2, 4, 6, 10, and 20, you can just put your R 5, 5, 5, 5, 5, all cases. And then you can find out what would be your R by Z. So these are the value. Actually, this column is nothing but this column divided by this column here, okay? Once you get that R by Z here, then actually you can either get that I1 value directly from the table, or you can just use the equation. That's up to you. This is very simple equation. I think like when you are doing that problem in Excel, then basically you can just set the equation and find out your I1 from there, okay? Now you can see here, let's say for example, your R by Z equal to 2.5. So when this one is 2.5, here, 2.4 and 2.6, I don't have 2.5. So you have to take the, like interpolate that one. And this is basically the middle of this one, right? So 0040 and 0029. This is like 0.00345. So that's the value they used here, 0043, oh no, 0034, okay? Similarly for 1.25, 0.083, and these are the problem, like you may not have that value directly. Let's say for 0.83, you may not have the actual value there in the table, okay? So you might have to like interpolate that one. But sometimes it's much easier to set that one in your Excel and set the actual equation of your I3 and find out the data directly from there. Once you get that one, then basically your del sigma Z is equal to P divided by Z square I1. So basically this one is P, which is actually 5 kilonewton divided by Z square, and then I1, which is this column here. So if you set that one, then basically you can get the answer from here. So you can see that 0 here, the change in effective stress is 0. Then basically you were talking about like a distance, like here you can see this Z is changing here, but this one is actually 5 remains same. So you can see actually if you go down, this one is increasing. So what does it mean? This one means like, let's say here, if we apply like 5 kilonewton load here, at the surface actually doesn't have any impact, 0 impact for this load here, okay? If you go down, 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 then basically your impact would be more, okay? Then again, you will see that if you go down, this one will diminish, like again, okay? So that's what happens here. Now let's see, let's move forward. This one is vertical stress from a vertical line load. Line load, vertical stress increased inside the soil mass due to a vertical flexible line load of infinite length that has an intensity Q per unit length, can be determined as del sigma Z equal to 2Q Z cube pi X square plus Z square whole square. Now, you can see this is your X-axis, this is your Z-axis, and actually your Y-axis is just, like right angle through that board, okay? Through that board here. Now, your line load is along that line here in Y-axis, okay? You take that one in this way is your line load. What is actually line load? Like, let's say you are talking about a load from a wall, okay? That's a, even though this is not infinite, but actually you can definitely use that one as a line load, okay? So if you have a wall along that line here in the Y-axis, we are trying to find out like what would be your, like change in stress because of that line load here at point A, sorry, which is at a distance x from that y line at a depth of z here. So that's basically is given here. Now you can set that equation in your Excel sheet and you can find out that how this one is going to change because of the change of your z and x, okay? Also, you can write that one as this, like divide that one by z cube at the top and bottom, then basically you get del sigma z equal to 2q pi z x by z whole square plus 1 into square here, okay? So basically you use this one using that equation. Now, there is an example here. So this one is saying that the figure below, this one A, shows two line loads on the ground surface. Determine the increase of the stress del sigma z at point A, okay? So there is one line load, means let's say that there is one wall just perpendicular to this, like screen here. And there is another one which is parallel to this line here. So two parallel, walls. So you are trying to find out this one, which is 5 meters from one of their wall and the 10 meters from the other wall. And we are trying to find that out, that how the sigma z will change at a depth of 4 meters, okay? Now, basically, we can use the principle of superposition. Just consider like this figure is nothing but one force, this one here, which is 5 meters, that's your A, plus that 15 kilonewton per meter, this one, which is actually 10 meters from this point here. So if we try to see the effect at A because of this load plus the effect of this load here, and if we add them together, then basically we can find out the combined effect of these two line load, okay? So here you can see your del sigma z is basically del sigma z1 plus del sigma z2. One is for this one and 2 is for this one. So if you compute that one separately, del sigma z, then 2q1 z square pi x square z square, and then whole square. So you can see this is 7.5, your z is 4, here is x equal to 5, so you get 0.182 kilonewton per meter square. And then the effect for this one is basically 2 into 15. You can see this is now 15 into 4 because this z is at 4 and your x is now 10, okay? So from there, actually, you can see this is the impact for this one. Now you can see the impact here is much bigger than this one because this one is closer. This is only 5 meters from that point, okay? Here, this one is 10 meters from that point. So if you want to get the total effect from there, that's your del sigma z, you just add this together. So you have 0.227 kilonewton per meter square. So that's the change in vertical stress at point A because of these two line loads, okay? Now, there are many other situations that the book has discussed. We are not going to discuss everything. I'm just trying to show you how to use this formula and then how to find out, your change in stresses at different locations because of different type of loads, okay? So I'm just trying to cover only the most important ones that you have to encounter in the field, okay? Here is like, this one is the stress at any point below a uniformly loaded circular area, okay? That circular area could be a foundation of a column, or that could be, let's say, a water tank, okay, round shaped water tank, or some other kind of tanks, okay? So in that situation, we are trying to see that how we can find out, because of that load, which has an intensity of Q, and the radius of that load is uppercase R, we are trying to find out any location A, which is lowercase r from the center and at a depth of Z, okay? So in that situation, the change in your vertical stress at A because of this load here is Q multiplied by A prime plus B prime. Q is the intensity of load. A prime and B prime, these are function of Z by R and R by R, okay? So you can find that values of A prime and B prime in your book in table 10.7 and 10.8. I just tried to show that one here too, that this is basically your R by R. This is the distance from the center to the point at which I'm trying to find out my stresses. R is the radius of the circular, like loading or circular, foundation. Here, Z is the depth, and again, capital R is basically your radius of that circular slab. So this is the value of Z by R, and these are the value for R by R. Once you know that one, then basically this one is for A prime, okay? This table is for A prime. Similarly, you can get the values of B prime with Z by R and R by R. So this is Z by R and this is R by R. So you can just find that value from here, okay? Now let's see an example here, which is saying, consider a uniformly loaded flexible circular area on the ground surface as shown in figure 2, okay? Given R equal to 3 meters. From here to here is 3 meters. Uniformly load is Q equal to 100 kilonewton per meter square. Here, the load is coming from the structure. Let's say this is the foundation. Then calculate the increase in vertical stress at a depth of 1.5 meter, 3 meter, 4.5 meter, 6 meter, and 12 meter below the ground surface for points at R equal to 4.5 meter. Okay, so these is actually outside of that one. Okay, this is 3 and this is actually 4.5. And then you go at a different depth. They are asking not for one depth, they are asking like, hey, how this one is going to change. Okay, so from that equation, you can just find out your R by R, lowercase r divided by capital K's is 4.5 by 3. So that's actually 1.5. Now, this is your Z. We just prepared that table here. That Z at 1.5, 3, 4.5, 6, and 12, that's they are asking you to find out, okay? So if you try to see like if your Z is this, R is kind of fixed, which is 3 meter. So Z by R is this, okay? 0.5, 1, 1.5, 2, and 4. Now you have to find out like for Z by R for any particular value and R by R is equal to 1.5, which is fixed, that what would be your A prime and B prime. Once you get your A prime and B prime, you just set that one in that equation here and you get your del sigma Z, okay? Now, if I go here, you can see that my R by R, they said like what is actually 1.5 fixed, then I can see that 0.5, then 0.1, and then 1.5, 2, and 4. So basically my A prime would be like this one, this one, this one, this one, and this one, okay? So that's what we have here. Let's see here, that's your A prime, okay? So first 1.5 is 0.095. They just took like 3-digit here, 0.95. You see here, actually, the first one is not 0.95, it's 0.9499, but they just took like 3-digit. I think that's quite reasonable, okay? So similar way, I can just go to my table here for B prime, and then I know my R by R is basically 1.5. And then again, I try to get the Z by R equal to 5, 1, 1.5, 2, and 4, okay? So I see that this one and this one goes here. So this one is negative, and this is 1, 2, 3, 4. These are positive here, okay? So that's basically you can see here. Oh, just 1 second. So you can see this one is negative and the other 4 is positive. Once you plug that A prime and B prime in that equation here, your Q is given, which is 100 kilonewton per meter square. Then you will see that this one is like this. So at 1.5 Z here, somewhere here, which is 6 kilonewton per meter square, then here is 12.6, here is 13, here is 12.7, here is 6.5, and then if you go further, then actually you will see at a certain depth, this one will completely diminish, okay? Anyway, so let's move forward. Now, one other thing, let me say that one, like sometimes they have another one just to find out the load, not at any point, but at the center, okay? Usually the center has the highest, impact, okay, along the center. So in that situation, if you just want to find out anything along the center line here, then basically your R, lowercase r, has to be 0, okay? So here, this one has to be always 0 here, okay? And then you can just change this one and this one based your A1, A prime and B prime has to be changed because for R by R has to be 0 here, okay? Then you will just get the, the answer from there. And you will see that actually at the center has the highest impact for this particular load. Okay, as you go away from that load, the impact goes smaller and smaller. Okay, as you go down, then the impact goes smaller and smaller. Okay. Now let's see, like this one is the most important one, the stress below at the corner. You see, like this is a rectangle load. Most of the cases, your foundation for any column or any building is usually rectangle, okay? That's why this one is extremely important, that if you put the column footing on top of the soil or like a little bit 3 feet below the soil, then how this load is going, like down, how this one is going to propagate with the depth, okay? So here you can see, let's say this is a rectangle load here, which has the load intensity is Q. Then at the corner of this rectangular load has to be del sigma Z is actually Q into I3, okay? I3 is something which can be like, it's a big number here, but again, you can just plug that one in your Excel sheet and find out what would be your I3 by changing your M and N. Now, what is M and N? M is basically B by Z. B is the width, and N equal to L by Z. L is the length. Now, which one is length and which one is width? Length is always bigger than the width. So if you have any dimension, you always pick the bigger one as your L and the smaller one as your B, okay? So the variation of I3 with M and N is given in the next table here. So you can see this is your N and this is your M. So you can find out that the value of your I3 from your M and N, okay? Now, this one is actually talking about if you want to find out the change in stress at the center of any rectangular load, okay? Actually, you can use that one, this same formula to find out at the middle, because you can, I'll just explain that one later on. Let me finish that one first, okay? So here, this one is saying that del sigma Z at the center or middle point of the rectangular loading is Q into I4, okay? And I4 is basically this one here, which is nothing but a function of M1 and N1, okay? Now, what is M1? M1 is equal to L by B, N1 equal to Z by B, okay? And small b is basically the width B divided by 2, okay? Now, the variation of I4 with M1 and N1 is given in table in the next page. So that's the M1 and N1 value. If you have that one, then basically you can find out your I4 directly from there, okay? Now let's see an example here. This example is saying that the plan of a uniformly loaded rectangular area is shown in figure 1030A, actually this one here. Determine the vertical stress increase del sigma Z below the point A prime here at a depth of Z equal to 4 meters, okay? So basically this one is my rectangular loading. This is the plan, okay, plan view. So the intensity of that load is 150 kilonewton per meter square, but I try to find out at a location of that point A prime, which is along that line here, 1 meter outside from that corner, and at a depth of 4 meters, okay? Now you can see here that from the, like previously we just tried to see that actually if this is your rectangular load, then I can only find out the stress below at the corner or just at the middle, right? Now, if I think that this is the corner, so what I can do, I can just expand that one up to this point, okay? This one, and then I subtract this part here, okay? If I take this one and then take this one out from there, that would be like this one. Why I'm trying to do that one? Because when I'm just extending that one now, my A prime is the corner. So I can use the formula to find out the change in stress at the corner of that loading here. And again, where I'm gonna subtract this part here, you can see A prime is at the corner. So basically I can use the formula for corner, like QI3, okay? So let's move forward. So the stress increase del sigma Z can be written as del sigma Z for the longer one minus del sigma Z because of the shorter one, like here. del sigma z because of this slab minus del sigma z for this particular, like rectangular loading, okay? So that's what we are trying to do. So we can just do that one separately for this one and this one. So for the bigger one, you just try to see your m and n. So m equal to b by z and n equal to l by z. If you go back there, then basically this is 4, l is 4, b equal to 2, and z equal to 4, okay? L equal to 4, z equal to 4, and b equal to 2. So if you go here, you can see 2 by 4 and 4 by 4, so m equal to 0.5 and n equal to 1. So from that figure, m equal to 0.5 and n equal to 1, the value of I3 is actually 0.1225, okay? So the del sigma z equal to q into I3, so q equal to 150 and I3 equal to 0.1202. So we can see this is 18.38 kilonewton per meter square, okay? Now you can just go back there and try to see like m equal to 0.5 and n equal to 1, your I3 equal to 0.1225. If I just go back there, m equal to 0.5 and n equal to 1, you just go back to the table here. That's your I3. So n equal to 0.5 and m equal to 1. So actually this one here, right? No, this one. So that's 0.1202. Actually, I think I just got the wrong one. M has to be 0.5 at n equal to 1. So I3, let me go back here. So that this one has to be actually 1. And this one has to be 0.5. So this one is here, 0.1202, okay? So what's happening here? Actually, this one is m equal to 0.5, n equal to 1. Anyway, there might have like, yeah, they wrote that one, but you see like here actually use 0.1202. Okay, so this one is wrong. That has to be 0.1202. So for this one is basically, you can see 18.38 kilonewton per meter square. Now we'll try to find out this one here, okay? So again, for that area, your B by Z, that's equal to 2 by 4 and N equal to L by Z. So we are talking about now this area here. So your L is now 2 and B equal to 1. As we said earlier, the bigger one is always L and smaller one is always your B. So this is your L, this is your B, and this is your Z4, okay? So if we go there, then B by Z equal to 1 by 4, which is 0.25, and N equal to 2 by 4, which is 0.5. And if we go through that table here, and we try to find out what is my I3, so here I3 is 0.0473, hence you can see your del sigma Z for second, like loading area is 7.1 kilonewton per meter square. So the actual, let's say, the actual change in stress is this minus this. So 18.38 minus 7.1, that's actually 11.28 kilonewton per meter square. Now I wanted to discuss that, like sometimes don't need that I4 thing. You can just calculate from I3 here. Now how how this one can be changed. You can see if I want to find out the center here at the middle of that point, then I can just divide that one like 4 rectangle passing through that point here. And you can see this middle point is actually the corner of all these 4 small rectangles. Okay, so if I see what would be the effect at this point because of this one rectangle, then I can just quadruple that to make like what would be the impact from 4 small rectangle at the middle of that point. Okay, so we can also, rather using like QI4 equation, we can also use that QI3 equation, just like change my L and B, because my L would be L by 2 and B would be B by 2 at that time for that 4 small rectangle. Okay, but that's up to you. If you feel more comfortable with the other one, you are just most welcome to do that. Now, I would like to thank all of you to listen, like that video. And if you have any question, please don't forget to join me in the Zoom session. And we can definitely discuss that one there too, okay? Thank you so much. I appreciate your attention. Bye.